What does it mean to ask what came before the beginning? If time itself started with the Big Bang, then the very word before begins to unravel. It's like asking what lies north of the North Pole. The question feels natural, but the answer slips away as soon as you try to hold it. Still, this is where our curiosity leads us, to the paradox at the edge of everything we know. And before we dive deeper, I'd love for you to do something simple. In the comments, share where you're listening from, the city, the time, maybe even the feeling you're in right now. It's a gentle reminder that though we're scattered across the world, we're gathered here in one shared moment of wonder. And if you'd like to support this small but growing circle, consider subscribing. We've set a quiet goal of reaching our first 10 listeners who choose to stay. It may be a tiny number, but every one of you helps turn this into something real. Now let's return to the puzzle. The Big Bang is often described as an explosion, but it wasn't a fireball bursting into space. It was the expansion of space itself, a sudden stretching of the very fabric of reality. Imagine a balloon inflating. Not because something is poured inside, but because its surface is stretching in all directions at once. Every point moves away from every other, not into empty space, but into new space being created in the act of expansion. That expansion did not just give rise to galaxies and stars, it gave rise to time itself. And this is where the paradox becomes sharp. We ask what existed before, but if time had no existence before the Big Bang, then the question dissolves. There may not have been a before. The Big Bang might not be the start of a story, but the edge of a page, the place where the book itself begins. And yet human beings rarely settle for that. We are creatures of beginnings. Every story we tell starts somewhere. Every journey begins with a first step. So when cosmologists say there was no before, the mind resists. It wants to press further, to imagine something behind the curtain, a cause behind the cause. Was there a hidden state before the universe we know? Was there another cosmos, another cycle, another kind of time altogether? We don't know the answers. Perhaps we never will. But to sit with this question is to touch the very edge of imagination. The Big Bang is not just a moment in physics. It is a mirror for our hunger to understand. And so this is where we begin our journey tonight. Not with certainty, but with wonder. The paradox of before will follow us through philosophy, through physics, through speculation, and through silence. So let's take a breath, let's slow down, and let's begin. Time as a human illusion. Time feels so obvious to us that we almost never question it. We wake up, the morning becomes afternoon, the sun sets, and we watch the day slip into night. Our lives are measured in calendars, birthdays, and memories. It feels like a river flowing endlessly forward, carrying us from one moment to the next. But when physicists and philosophers examine time closely, the illusion begins to unravel. Einstein showed us that time is not separate from space but bound to it. Together they form space-time, a fabric that bends and curves under the weight of matter and energy. What this means is that time does not tick the same everywhere. A clock on a mountain runs faster than one at sea level. A clock on a satellite moves at a different rhythm than a clock in your pocket. Astronauts in orbit experience time slightly differently from the people they left on Earth. Time is not universal. It is personal. This alone is enough to unsettle our everyday sense of reality. But it goes deeper. At the level of quantum mechanics, time does not even appear as a fundamental ingredient. Instead, what emerges are relationships, correlations between events, and time is something we impose on those patterns. Some physicists suggest that time is not a thing at all, but a story we tell ourselves about change. In other words, time may not exist in the way we think it does. Consider how memory works. You remember yesterday, but not tomorrow. That gives you the feeling of time moving forward. Yet physics does not prefer forward over backward. The equations describing particles, energy, and motion work just as well in reverse. From the viewpoint of the laws of physics, time is symmetrical. The arrow we feel, always pointing toward the future, may arise only because entropy or disorder tends to increase. In this sense, Time is not a flowing river, but a measure of change in patterns of energy. This raises a haunting possibility. If time is not fundamental, then asking what happened before the Big Bang may be asking the wrong question altogether. Before only makes sense if time is real in the way we imagine it. If time is emergent, then perhaps the Big Bang was not a beginning, but a transformation from one state into another, in which time as we know it crystallized into existence. Philosophers have long suspected something like this. Saint Augustine, writing more than 1,500 years ago, remarked that time itself was created with the world. To ask what God was doing before creation, he wrote, is meaningless because before only exists inside creation. The wisdom of that idea echoes in modern physics. If time began at the Big Bang, then asking what came before is not a puzzle of missing knowledge. It may be a puzzle of language, one that reveals the limits of human imagination, and yet, even if time is an illusion, it is a powerful one. We feel it in our bodies. We watch it in the cycles of nature. We sense it in the slow wearing away of mountains and the sudden flash of lightning. Time, whether real or emergent, shapes the way we live. The paradox is that it may not exist at the deepest level of the universe, but it defines everything about our experience of it. So when we press on the question, what came before the Big Bang? We are not just asking about physics. We are asking about the very structure of perception. We are asking whether time itself is the stage of existence or just a trick of the mind. And that brings us to an even older conversation, one that began long before Einstein, long before quantum mechanics. Because humanity has wrestled with the question of eternity for thousands of years. Let's turn now to those ancient voices and see how they shaped the riddle of beginnings. Ancient views on eternity long before telescopes, satellites, and physics equations, humans looked at the night sky and asked, has this always been here? Or did it begin at some point? The question of eternity is not new. It stretches back into the oldest myths, the earliest philosophies, and the first recorded reflections of human thought. In ancient Greece, Aristotle argued for an eternal universe. To him, the cosmos had no beginning and no end. Motion, change, and the heavens above were everlasting. The idea of creation out of nothing made no sense to him because he could not imagine something arising without a cause. If there was a universe now, he reasoned, there must have always been one. For Aristotle, eternity was the natural state. Other traditions saw things differently. In the Hebrew scriptures, the universe had a definite beginning, a creation spoken into existence. Time and matter were not eternal, but gifts of a divine will. In early Christianity, thinkers like Augustine wrestled with this idea. He famously declared that time itself began with creation. To ask what came before was meaningless because before could only exist inside the flow of time, not outside it. His insight is surprisingly close to what modern cosmology suggests, that the Big Bang was not just the birth of matter and energy, but of time itself. In India, Hindu philosophies leaned toward cycles rather than singular beginnings. The cosmos, they taught, expands and contracts in great ages, endless rhythms of birth and destruction. In Buddhism too, the universe was seen as without a beginning, a chain of causes stretching infinitely back. These ideas of cycles and eternal recurrence echo strikingly in today's cosmological models of bouncing universes and repeating epochs. Even in more recent centuries, philosophers could not agree. Immanuel Kant declared that reason breaks down when we ask whether the universe had a beginning or not. Both options, a universe with a first moment or one stretching back forever, seemed impossible to accept and impossible to deny. He called it an antinomy, a contradiction at the heart of human reason. What's striking is how these ancient and medieval ideas already map onto the tensions we still face today. Some saw eternity as natural, others saw beginnings as necessary. Some thought time was an illusion, Others thought it was the most fundamental fact. Thousands of years later, with satellites mapping cosmic radiation and physicists probing quantum theory, the paradox remains, and this tells us something important. The question of before the Big Bang is not just about physics. It is about the human need to frame reality with beginnings, endings, and cycles. Our minds resist the idea of timelessness, so we invent stories of eternity or creation to make sense of it. Now, with Einstein's revolution and the birth of modern cosmology, we can return to this ancient puzzle with new tools. Physics may not resolve the debate fully, but it reshapes the terms of the question. What if the Big Bang is not a point in space, but the edge of time itself? Einstein's fabric and the edge of time. Imagine standing on a quiet shore, watching waves roll in. You know the ocean is vast, but the line where the sea meets the sky feels like an ending, a horizon you cannot cross. Einstein taught us that the universe has its own horizon, woven not of water and air, but of space and time themselves. Before Einstein, time was thought to be absolute, a cosmic metronome ticking the same everywhere. But he showed us that time stretches and bends. A clock on Earth's surface ticks slower than one high in orbit. A moment near a black hole can last a lifetime compared to a moment far away. Time is not steady. It is flexible, molded by gravity, sculpted by energy. And this means something extraordinary about the Big Bang. It was not an explosion inside space. It was the stretching of space itself. It was not a fireball burning inside time. It was the birth of time. Asking what the universe expanded into is like asking what's outside of everything. There is no outside. The expansion is the stage itself being built. Think of the North Pole. It is the furthest north you can go. To ask what lies further north is a trick of language, not a real question. The Big Bang may be like that. Not an event in time, but the edge where time itself begins. Still, our minds rebel against this. We are wired to think in cause and effect. This happened, then that followed. We cannot help but imagine a before. What caused the first spark? What set the fuse burning? Einstein's equations take us close to the answer, but at the very beginning, they fail. At the singularity, density becomes infinite and the fabric of spacetime folds in on itself. The math collapses, and we are left staring into mystery. It is here that physicists had to dream beyond Einstein. If time has an edge, what lies beyond it? If the beginning is also a boundary, is there a way to imagine a universe that starts without ever truly beginning? That question gave rise to one of the boldest ideas in modern cosmology, a universe finite yet without edges. A universe that does not start with a bang, but with a smooth, timeless unfolding. The no-boundary proposal. What if the universe has no sharp beginning at all? That was the daring thought of Stephen Hawking and James Hartle when they introduced what is now called the no-boundary proposal. To understand it, imagine standing on Earth. If you walk north, the lines of longitude guide you closer and closer until they meet at the pole. But when you reach the North Pole itself, there is no further north to go. It's not that the Earth ends there. It simply curves smoothly into a new direction. The pole is a boundary in name, but not in reality. Hawking and Hartley suggested the universe might be the same. At the beginning, time did not slam into a wall. Instead, it curved gently, like the surface of a globe. The Big Bang would not be a hard edge, but a smooth transition. A place where what we call time emerges naturally without requiring a before. This idea reshapes the puzzle. If the universe is finite but without boundaries, then the demand for a first cause weakens. There is no sudden cliff where nothing turns into something. Instead, reality rounds itself off like a sphere where every point is part of a continuous whole. Of course, this is not the universe we walk through every day. We experience beginnings and endings everywhere. The rising and setting of the sun, the first breath of a child, the last breath of a life. It is almost impossible to imagine existence without a starting line, and yet the no-boundary proposal suggests that the cosmos itself may never have had one. Critics point out that this is, for now, a mathematical model, not a proven description. But even as an idea, it carries power. It offers a universe that does not need something outside itself to set it in motion. A universe self-contained, without edges, without before. It's a concept that sounds abstract, even dreamlike. But it may also be the simplest answer to the most difficult question. Instead of asking what came before time, perhaps the truth is that time emerged smoothly, like a dawn without a night. And if that's the case, then our search must continue in another direction. Because if the universe has no boundary, perhaps it does not just exist once. Perhaps it moves through endless cycles, breathing in and out forever. Cyclic universes and cosmic rebirths. Picture the rise and fall of your own breath. Inhale, pause, exhale. Then it begins again. Some cosmologists have wondered if the universe itself might follow a rhythm like this, expanding, contracting, and rebirthing endlessly. This is the idea of cyclic universes. Instead of one singular beginning, reality would be an eternal heartbeat. Our Big Bang would not be the first, but simply the most recent pulse in an infinite chain. Each universe would swell with galaxies, burn with stars, and eventually collapse under its own gravity, only to ignite again in another Big Bang. The thought is both comforting and dizzying. Comforting because it frees us from the riddle of before. If the universe has always cycled, then there is no need to imagine a creation out of nothing. Dizzying because it stretches the story of existence far beyond what we can observe. Ancient traditions imagined cycles long before physics did. In Hindu cosmology, the cosmos moves through vast ages of creation and destruction. In Buddhism, worlds rise and fall without a first cause. These echoes resurface in modern science through the mathematics of contraction and bounce. Some models suggest that after billions or trillions of years, dark energy could reverse, pulling everything back together in a big crunch. When densities become extreme, space-time might rebound, triggering a new expansion, a new Big Bang. Others propose that collisions of higher dimensional objects could set off repeating bursts of creation. But there is a subtle beauty hidden here. If universes are born and die in cycles, each one may inherit faint traces of the last. Just as memories linger between breaths, the patterns of one cosmos might echo into the next. Ripples in the cosmic background, strange alignments in the structure of galaxies. Some physicists have wondered if these are whispers of past universes bleeding into ours. Of course, the evidence is uncertain. These are still speculative models. But the very possibility is enough to shift perspective. Perhaps the Big Bang was not a beginning, but a transition. Perhaps we live not in the first universe, but in the latest chapter of an eternal cycle. And if cycles exist, then maybe our cosmos is not alone. Maybe beyond our sight or before our time, entire other realities have already risen and fallen, leaving us suspended in just one moment of a greater rhythm. Brain collisions in higher dimensions imagine that our universe is not the whole story, but a sheet, a vast invisible membrane floating in a higher dimensional space. This is the picture suggested by certain versions of string theory. They call these membranes brains, and if there are many of them, drifting side by side in dimensions we cannot see, then our Big Bang may have been something far stranger than we imagined. In this vision, universes are not isolated. They are neighbors layered like pages in a book. Most of the time they are silent, unseen, separate. But what if, from time to time, two brains collide? The energy released in such a collision could ignite a new cosmos, filling it with matter, radiation, and the expansion we call the Big Bang. Think of cymbals in an orchestra. They remain still, quiet until they crash together. The sound rings out, then fades. Some cosmologists propose that our universe is the ringing aftermath of such a cosmic clash, not the start of everything, but the echo of two unseen dimensions brushing against one another. It is an idea almost impossible to picture. Higher dimensions are beyond our senses. We cannot see them or touch them. Yet mathematics suggests they may exist, curled up invisibly at tiny scales or stretched vast in ways that only gravity can feel. If so, then our universe might be only one surface in a far larger, multidimensional reality. This theory is sometimes called the ekpyrotic model, from the Greek word for conflagration. It suggests that Big Bangs may not be rare. They may happen again and again each time brains meet. That would mean our universe was born not out of nothing but out of contact, a cosmic touch in a space far beyond our imagination. Of course, this is speculative and evidence is scarce, but the idea itself is enough to stir awe. It hints that what we see, galaxies, stars, even the flow of time, may be just one layer in a stack of countless others. Our cosmos may be ordinary in a landscape of universes colliding, separating, and colliding again, and if that is true, then before the Big Bang takes on a new meaning. It may not have been nothingness at all, but another universe drifting close, waiting to collide. The reverse time universe. We take it for granted that time flows forward. You wake, you live the day, you sleep, and tomorrow follows. But physics doesn't actually require time to move this way. The equations work just as well if time runs backward. The forward arrow we feel may be an illusion born of memory and entropy. Which leads to a bold idea. What if the Big Bang created not one universe, but two, mirror images of each other, with time flowing in opposite directions? In this picture, the Big Bang is the central point, a kind of cosmic mirror. On one side lies our universe, expanding forward in time. On the other side lies a twin, expanding backward. From our perspective, their time runs in reverse. From theirs, we are the ones who move backward. Both are valid, both are consistent, but each forever sealed from the other by the singular moment that birthed them. It is a disorienting thought. Imagine an entire cosmos where stars still form, galaxies still grow, and beings might live lives as vivid as ours, but their sense of past and future runs opposite to ours. To us, they would seem to be unmaking. Their universe, collapsing order into a tighter and tighter beginning. To them, we would appear the same. This idea is not fantasy. It arises naturally when physicists try to make sense of time around the Big Bang. If the laws of physics do not care about forward or backward, then perhaps both emerged. Perhaps the Big Bang was a branching point, giving birth to twin arrows of time, each flowing away in its own direction. And here is the haunting beauty. If that is true, then the Big Bang was not just the beginning of our story, but the middle of a larger one. Two universes, back to back, expanding away from the same moment, like reflections on either side of a mirror. We will never meet this reverse time universe. Its arrow of causality forever prevents us from crossing, but simply imagining it expands our sense of possibility. Time itself, the thing we trust most, may not be a universal truth. It may be just one direction chosen by chance, mirrored by another flowing the other way. So when we ask what came before our Big Bang, the answer might be astonishing. Another universe did, one that we can never see, where time itself runs the other way. The quantum nothingness. When we think of nothing, we imagine emptiness, a silent void, dark and bare. But in the strange world of quantum physics, nothingness is never truly empty. Even in a perfect vacuum, particles flicker in and out of existence, borrowing energy from uncertainty itself before vanishing again. What seems like nothing is, in fact, a restless sea of possibility. Some physicists suggest that the Big Bang could have sprung from this kind of quantum nothing, not from an explosion of matter in space, but from the spontaneous fluctuation of the vacuum itself. In this view, the universe is not born from a cause, but from probability. Out of countless tiny fluctuations, one grew large enough to ignite expansion. Our entire cosmos, with its galaxies, stars, and minds, may be the outcome of a random spark in a field of nothing. It sounds improbable, but probability itself works differently on cosmic scales. Even if the chance is unimaginably small given infinite time, the unlikely becomes inevitable. A quantum vacuum could sit timelessly, not changing, not moving, until, through a fluctuation, a universe bursts forth. But here lies the paradox. If time itself begins with the universe, then what does it mean to say the vacuum waited for a fluctuation? Waiting implies time, and yet the proposal suggests a timeless sea giving birth to time itself. To picture it, imagine a still pond. On the surface, ripples are absent, pure calm, then suddenly a wave forms, not because something struck the pond, but because the possibility for a ripple was always hidden inside the stillness. That ripple is the universe. In this sense, nothingness is not absence. It is potential, a womb of physics, invisible but pregnant with possibility. What we call nothing may actually be the deepest kind of something, a background that can, without cause, give rise to all causes. It is a difficult concept to hold. Our intuition insists that something must come from something, but quantum physics undermines that certainty. Particles can appear without warning, energy can fluctuate without cause, reality can blink in and out as if existence itself is optional. If the universe emerged from such a state, then before loses its meaning. There was no before, only potential. And perhaps this is the most unsettling truth of all, that the universe may not have required a reason. It may exist simply because, in the strange logic of quantum mechanics, existence itself is one of the possibilities written into the fabric of reality. Eternal inflation and the multiverse. In the first fraction of a second after the Big Bang, the universe may have expanded faster than the speed of light. This idea is called cosmic inflation, and it explains why the cosmos appears smooth and uniform in all directions. But inflation might not have ended everywhere at once. Some regions may have stopped inflating, forming universes like ours, while others continued expanding endlessly. If so, then creation never truly stopped. It still goes on, forever budding off new universes in a vast cosmic foam. This is the idea of eternal inflation. Our observable cosmos would be just one bubble among countless others. Some bubbles may be small, others infinite. Some may expand like ours, others collapse quickly. Each one would be sealed from the others by the runaway expansion of space between them. We will never see across that gulf, never touch those other universes. But their existence may still be real and their number without limit. The thought is overwhelming. Imagine a tree that grows forever, each branch budding into new blossoms. Our universe would be just one flower among uncountable others. Or imagine an ocean where bubbles constantly rise and pop, each one a universe with its own physics, its own galaxies, perhaps even its own forms of life. What makes this idea powerful is not just its poetry, but its mathematics. Inflation predicts variations in the energy of space, and those variations naturally lead to regions where inflation continues. In this way, eternal inflation is not an added idea, but a consequence of the theory itself. If inflation happened, it may still be happening, out there beyond our horizon. This has a radical implication. When we ask, what came before the Big Bang, the answer might be, another universe did, and before that, another still. Not in a linear chain, but in a vast branching multiverse, where beginnings are local, but creation itself never ends. The multiverse challenges our sense of uniqueness. We like to think our cosmos is special, the one stage where stars shine and life arises. But eternal inflation suggests there could be endless variations. Universes where gravity is stronger, where atoms never form, where light never shines. And perhaps universes much like ours, where beings look up at their skies and wonder the same questions we ask now. We will never see those other universes. They are hidden beyond the speed of light, forever cut off. But the possibility itself reshapes our imagination. The Big Bang may not have been the beginning of everything. It may have been the beginning of our bubble, one bloom in an infinite, eternal multiverse. The arrow of time and entropy. Everywhere we look, time seems to flow in one direction. Eggs crack, but never uncrack. Smoke rises, but never falls back into the flame. We grow older, never younger. This one-way flow is called the arrow of time, and it is tied to a principle called entropy, the natural tendency for systems to move from order to disorder. But here is the puzzle: if the universe began in the Big Bang, why did it start in such an improbably ordered state? Entropy should increase over time, which means the past should be more ordered than the present. And yet the early universe was astonishingly smooth and uniform, filled with matter and energy spread evenly across space. It was a cosmos at low entropy, balanced like a freshly set stage. This is not what we would expect by chance. The odds of such a smooth beginning are staggeringly small, and yet it is precisely this low entropy start that allows the arrow of time to exist. Without it, there would be no distinction between past and future, no irreversible flow, no unfolding story. Some physicists propose that entropy itself is what defines time, that the future is simply the direction in which entropy increases. If that is true, then asking what came before the Big Bang may be meaningless, because without a lower entropy state to contrast against, the very idea of before dissolves. The arrow of time begins only when entropy begins to rise. Others suggest that the multiverse may solve this riddle. In a sea of universes, some may begin in high entropy and collapse quickly, while others begin in low entropy and evolve into long-lived cosmoses like ours. In this view, our universe is not typical, but one of the rare few where order at the start allowed complexity, life, and memory to exist. The arrow of time is more than a scientific puzzle. It is the thread of our lives. It is why we remember the past, but not the future, why we feel the weight of aging, why history unfolds instead of standing still. To think that it all rests on the initial state of the universe is humbling. A single, improbable beginning gave rise to every story ever told, every breath ever taken, every moment ever lived. So when we ask what came before the Big Bang, one answer may be nothing, because before requires time, and time requires entropy. The arrow began there, and only then did before and after come into being. Beyond the cosmic horizon, when we look into the night sky, we are not seeing space as it is now. We are looking back in time. Light takes billions of years to cross the cosmos, so every galaxy is also a memory. But even light has limits. Beyond a certain distance, photons have not had enough time to reach us since the Big Bang. That boundary is called the cosmic horizon. The horizon is not a wall. It is not the edge of space. It is simply the limit of what we can observe. Beyond it, galaxies continue, stars burn, clusters form, but their light is forever out of reach. The expansion of the universe stretches space faster than light can cross it, so those distant regions recede eternally. They exist, but for us, they might as well be invisible. This means that our observable universe, the bubble of reality we can see, is only a fraction of the whole. The actual universe may be vastly larger, perhaps infinite. Our maps, our telescopes, our grand surveys are not portraits of everything, but tiny snapshots. As if we lived in a single room of a house, too large to ever walk through. And here lies the connection to the Big Bang. When we ask what came before, part of the difficulty is that our horizon hides the answer. If there were events before time as we know it, their signals may be smeared beyond the edge, unreachable forever. Some hints may remain. Tiny ripples in the cosmic microwave background, strange alignments in galaxy distributions. But the full picture lies past the horizon's veil. Yet this ignorance is not empty. It is alive with possibility. Maybe other regions of the cosmos operate under different laws of physics. Maybe vast structures beyond our sight tug subtly on our galaxies, like unseen giants pulling on invisible strings. Maybe entire other universes drift just past the curtain, separated not by distance but by expansion itself. To live inside an observable bubble is both humbling and inspiring. Humbling because we will never know the full story. Inspiring because it reminds us that mystery is not an accident. It is built into the structure of reality. The horizon is not just the end of sight. It is an invitation to imagine. So when we look up at the night sky and wonder what came before the Big Bang, we may also be wondering what lies beyond our horizon. The two questions are bound together, each pointing to the same truth, that what we see is only a fraction, and what lies beyond may be stranger, vaster, and older than we can conceive. Primordial black holes as relics of before. When we think of black holes, we imagine the death of stars, massive suns collapsing under their own weight until no light can escape. But some black holes may be far older than stars, older even than galaxies. They may be primordial, formed in the chaos of the first fractions of a second after the Big Bang. In that early era, space itself churned with fluctuations. Some regions were slightly denser than others. If a patch grew dense enough, gravity could have crushed it instantly, before atoms, before stars, into a black hole. These primordial black holes would be relics of conditions so extreme that no laboratory on Earth could ever reproduce them. Why does this matter for the question of before? Because if we can find these ancient black holes, they may carry imprints of physics that existed at the very edge of time's beginning. They would be fossils of creation, silent messengers from a moment when the universe was hotter, denser, and stranger than anything we know. Some could be tiny, no larger than mountains, yet as heavy as entire planets. Others could rival the mass of stars lurking invisibly across the cosmos. If they exist in large numbers, they might even explain dark matter, the invisible substance that outweighs normal matter 5-1. In that case, much of the universe's hidden mass would be made not of exotic particles, but of ancient scars left over from the dawn of time. Detecting them is difficult. They emit no light, reveal themselves only through gravity. But their fingerprints may be subtle. In the bending of starlight, in the quiet tug on galaxies, in the ripples of gravitational waves. If we can catch those signals, we might glimpse the universe not just after the Big Bang, but at the very conditions that birthed it. And here's the haunting possibility. If primordial black holes exist, some may have survived from an era before our own expansion. If the cosmos cycles, if universes rise and fall, then black holes could persist across the transitions. They could be the true immortals of reality, carrying memory from universe to universe. Whether or not this is true, the idea itself stretches our imagination. What we call the end of stars may also be the beginning of time, and hidden in the darkness of black holes may be the oldest evidence of what came before the Big Bang. The geometry of nothingness. When we picture the beginning, we imagine emptiness, a blank canvas waiting for creation. But mathematics suggests that even nothingness can have shape. Geometry does not require objects. It requires only relationships, curves, and dimensions. What if before the Big Bang there was no matter, no light, no time, only geometry? Physicists sometimes call this the pre-geometric state, a realm where space-time as we know it had not yet crystallized. Instead of flowing smoothly like a fabric, reality may have been a froth of quantum connections, a network without distance or direction. Out of this geometry, time and space themselves could emerge. The way ice emerges from water when the temperature changes. It is hard to imagine because our senses are tuned to things, stars, rocks, breaths, clocks. But geometry is pure structure. It is the skeleton of possibility. And just as music can exist without words, geometry can exist without matter. In this view, the Big Bang was not the creation of something out of nothing, but the transformation of pure geometry into space-time. Think of a circle. It has no edges, no beginning or end, yet it exists as a whole. Now think of a sphere, smooth and self-contained. Some physicists imagine the universe in similar terms. The cosmos may be finite but unbounded. It's nothing, a rounded geometry that contains everything without requiring an outside. This leads to a striking thought. Perhaps the reason we struggle to imagine before time is because time is not fundamental. It may be a property that emerges from deeper structures like temperature emerging from the motion of atoms. If so, then before is not the right question. The deeper truth lies in geometry, not chronology. Quantum gravity, the still unfinished theory that would unite general relativity and quantum mechanics, often points this way. It suggests that at scales smaller than atoms, space-time dissolves into a granular, probabilistic foam. The smooth fabric of Einstein is only an approximation, like a map of a land that hides its rugged detail. At the very beginning, the universe may not have been a place at all, but a mathematical possibility unfolding into reality. So when we ask what came before the Big Bang, one answer is this: geometry itself. No stars, no galaxies, not even time. Only shape, structure, potential. The silent framework from which existence unfolded. Echoes of other universes, the Big Bang may have marked the beginning of our universe, but what if traces of other universes still linger in the sky above us? Some physicists have proposed that faint anomalies in the cosmic microwave background, the afterglow of the Big Bang, could be scars left behind from collision. With other universes, the microwave background is astonishingly uniform, but not perfectly so. Across its faint glow, satellites like WMAP and Planck have mapped tiny variations, ripples that seeded galaxies. Yet among them lie strange features, unusually cold spots, odd alignments and patches that defy simple explanation. Some scientists suggest these may be the fingerprints of cosmic events beyond our own universe, a kind of cosmic archaeology, where the relics of other realities are imprinted into our skies. One idea is that during inflation, our bubble universe may have brushed against others. Imagine soap bubbles forming in a sink. Occasionally they bump and merge, leaving thin scars where they touched. If universes are like bubbles in the foam of the multiverse, then their collisions could leave behind observable signatures, faint but permanent marks in the radiation that fills space. This possibility is thrilling because it offers a bridge between speculation and evidence. For decades, the multiverse has been a philosophical idea, hard to test. But if echoes of other universes are truly written into the cosmic microwave background, then we may already have data whispering that our cosmos is not alone. Still, the evidence is controversial. Some physicists argue the anomalies are statistical flukes, the kind of random noise that will appear if you look closely enough at a vast data set. Others insist the patterns are too persistent to dismiss. The debate continues, fueled by the possibility that our universe may carry the faint bruises of past collisions. Even if the signals prove uncertain, the idea itself lingers in the imagination. To look up at the night sky and wonder whether the faint glow of microwaves carries not just our story, but the stories of other universes brushing against ours, is to feel the scale of reality in a new way. So when we ask what came before the Big Bang, one daring answer might be this: other universes came before, and their echoes may still be written in the faintest light we can see. The vacuum energy. See, when we imagine empty space, we often picture a silent void, a blank canvas with nothing upon it. But quantum theory tells us that space is never truly empty. Even the vacuum is alive with invisible activity. Particles flicker in and out of existence, energy fluctuates wildly, and the fabric of reality hums with a background vibration. This restless activity is known as vacuum energy. What makes this profound is that vacuum energy may not just be noise in the background. It may be the very engine of creation. Some physicists propose that the Big Bang was not a singular explosion from nothing, but a phase transition in this quantum sea. Just as water can boil into steam or freeze into ice, the vacuum itself can shift states. The universe could have been born in such a transition. A sudden release of energy that expanded space at unimaginable speed. This idea connects directly to dark energy, the mysterious force driving the acceleration of the universe today. What if the same vacuum energy that gave birth to the cosmos is still with us, spread everywhere, pushing galaxies apart? That would mean the beginning of time is not a past event, but an ongoing process. Creation continues in the restless churn of the vacuum, unfolding across all of space. The numbers, however, pose a puzzle. Quantum theory predicts that the energy of the vacuum should be enormous, enough to tear the universe apart instantly. Yet what we observe is tiny by comparison, small but not zero. This mismatch, called the cosmological constant problem, is one of the deepest mysteries in physics. Why is the vacuum energy so faint? Why does it exist at all? And how can something so subtle shape the destiny of everything? Some theorists suggest that different universes in the multiverse may have different amounts of vacuum energy, and only in the rare ones where it is small can galaxies, stars, and life exist. Others believe that our understanding of quantum gravity is incomplete, and that a deeper theory will one day explain the puzzle. But here is the haunting part. If vacuum energy is eternal, then new universes could be budding even now, hidden beyond our horizon, each one born from fluctuations in the same invisible sea that gave rise to us. In this sense, what we call nothing may be the most fertile source of all. So when we ask what came before the Big Bang, one answer is this: the vacuum did. Not empty, not silent, but a sea of quantum energy, simmering with possibility, forever capable of giving birth to new worlds. The role of mathematics beyond time. What if the universe did not begin with matter or energy or even space? What if it began with mathematics? Some physicists and philosophers suggest that mathematics is not just a tool for describing the cosmos, but the very foundation of reality itself. In this view, numbers, equations, and structures exist outside of time, eternal and unchanging. The universe is one of countless possible mathematical patterns, brought into being not by a cause, but by the fact that it is consistent. Think of it this way. Triangles existed long before anyone ever drew them. The number pi existed before anyone calculated it. These truths are timeless. They are not invented. They are discovered. Now imagine that the entire universe is like that, a mathematical object, timelessly real, waiting to be expressed. The Big Bang would then not be creation in the ordinary sense, but the moment when one particular mathematical structure, ours, became physical. This perspective is called mathematical Platonism, after the philosopher Plato, who believed that abstract forms exist independently of the material world. In modern physics, it finds echoes in string theory, quantum mechanics, and cosmology, where the equations seem almost to have a life of their own. The universe behaves as though it is following mathematics not just as a rule, but as its essence. If this is true, then before the Big Bang may not mean anything physical at all. It may simply mean that the mathematical structure we inhabit had not yet unfolded into what we call time and space. Before time, there was timelessness. Before cause, there was logic. Before the cosmos, there was mathematics itself. It is unsettling, but also comforting. If reality is ultimately mathematical, then it cannot end. The physical universe may collapse, decay, or fade into heat death, but the equations remain, waiting for expression again. In this sense, the universe is eternal, not as matter or energy, but as truth. Of course, this raises questions. Why this mathematical structure and not another? Why a universe that allows galaxies, life, and thought, instead of a sterile one of pure chaos? Some suggest the anthropic principle. Only in universes with the right mathematical laws can observers arise to ask the question. Others argue that deeper mathematics may reveal why certain patterns are privileged. Whatever the answer, this idea reshapes our imagination. The Big Bang may not have been the beginning of existence. It may have been the moment when timeless mathematics stepped into time, when an eternal truth began to play itself out as reality. So when we ask what came before the Big Bang, one possibility is that nothing physical came before at all. Only mathematics, infinite and eternal, quietly waiting to become the universe. Cyclic universes and endless rebirth. The story of the Big Bang is usually told as a single beginning, a moment when time itself began and the universe burst into being. But what if it was not the first? What if our cosmos is just one in a chain of universes, each born from the ashes of the last? This idea of a cyclic universe stretches across cultures. Ancient traditions spoke of time as a wheel, endlessly turning with worlds rising and falling in great cosmic ages. Modern physics, surprisingly, has circled back to something similar. Some cosmologists propose that the Big Bang may have been not a beginning, but a bounce, the rebound of a universe that collapsed before ours. In these models, expansion does not go on forever. Gravity eventually halts it, drawing everything back together in a big crunch. But instead of ending there, the collapse triggers another Big Bang, igniting a new cycle of space and time. Each cycle could wipe away memory of the last, but still carry subtle imprints. Patterns in cosmic radiation, echoes of events from universes long gone. Another version, inspired by string theory, imagines that our universe exists on a three-dimensional brane floating in higher dimensional space. When branes collide, they unleash energy that looks to us like a Big Bang. If collisions happen repeatedly, then universes are born again and again in an eternal dance across dimensions. What makes the cyclic idea compelling is that it sidesteps the hardest question: why was there a beginning at all? If the universe has no true first moment but instead has always cycled, then existence itself may be eternal. The Big Bang would not be creation out of nothing, but a renewal, the next heartbeat of a cosmos without end. Of course, there are mysteries. If cycles are endless, why does the universe look as young and fresh as it does, instead of worn down by infinite repetitions? Some theorists suggest that entropy resets with each bounce, clearing the slate. Others argue that each cycle expands larger than the last, pushing disorder outward and leaving our observable universe clean. Whatever the mechanism, the idea resonates deeply. Instead of a straight line beginning at nothing, reality may be a circle, always turning, always renewing. When we gaze into the night sky, we may be seeing not the first universe, but just the latest chapter in an infinite story. So when we ask what came before the Big Bang, one answer could be simple and profound: another universe did. And before that, another, stretching back without beginning, forward without end. The mystery of quantum time feels like the most natural thing in the world. We live by its rhythm measured in clocks and heartbeats. Yet, when physics peers into the foundations of reality, time begins to blur. In quantum mechanics, the equations that describe particles work perfectly well without a built-in notion of flowing time. Instead, they describe probabilities and interactions, timeless states shifting according to rules of mathematics. This raises a haunting possibility. What if time itself is not fundamental? What if it is an emergent property like temperature or pressure, arising only when many quantum systems interact? In that case, the Big Bang may not have been the start of time, but the moment when time crystallized out of something deeper. A timeless quantum reality. Imagine a world where everything simply exists in relation to everything else, without before or after. A cosmic symphony frozen in possibility. Then as complexity grows, a sense of direction appears. Entropy increases, events unfold, memories form. Time, as we experience it, emerges like a melody drawn out of silence. Some theories in quantum gravity support this vision. They suggest that at the Planck scale, the unimaginably tiny scale where quantum effects and gravity intertwine, time may dissolve entirely. The equations describing the universe at that level have no arrow, no ticking, no progression. What we call the Big Bang may have been the moment when this timeless foam gave rise to the ordered flow of time we now inhabit. But here's the wonder. Even if time is emergent, it feels absolute to us. It shapes our lives, defines our choices, gives meaning to beginnings and endings. The very act of asking what came before the Big Bang shows how deeply the arrow of time is written into human thought. Perhaps that is the paradox. To us, time feels like the most solid part of reality, but it may be the most fragile, the most conditional. Born in the furnace of the early universe, it may one day dissolve again, leaving only the timeless sea from which it emerged. So when we ask what came before the Big Bang, one answer may be this: nothing came before, because before is a concept that only exists within time. Outside of it, there is no before, no after, only possibility, waiting to become. The final mystery. Why anything exists at all? We've traveled through theories of cosmic cycles, multiverses, quantum foam, and eternal inflation. Each offers a glimpse of what might have come before the Big Bang. But, in the end, a deeper question still waits in the dark. Why is there something rather than nothing? Physics can trace the story of the universe back to fractions of a second after its birth. It can suggest mechanisms, inflation, quantum fluctuations, vacuum energy, that might explain how the cosmos unfolded. But even if we solve those riddles, one mystery remains untouched. Why do the laws exist at all? Why is there a canvas on which reality can be painted? Some thinkers suggest that nothingness is unstable, that the laws of quantum physics make it inevitable that nothing gives rise to something. In this view, existence is not an accident, but the natural state of reality. Others push further, arguing that every possible universe exists and ours is just one among infinite variations. Still others invoke philosophy, suggesting that existence itself may be a brute fact, something with no cause, simply there because it cannot not be. It's a question that may never have a final answer, and perhaps that is its power. Because behind all science, behind all theories, lies wonder itself. The human impulse to ask, to reach, to imagine. The mystery of existence is not just about the cosmos. It is about us. Why we are here, why we can ask at all. Why we can look up at the night sky and feel both small and infinite. Maybe the truest answer to what came before the Big Bang is not a scientific model or a philosophical proof, but a reminder that some questions are meant to open us, not close. They invite us to live in awe, to carry wonder with us into each moment, like a quiet echo of the cosmos itself. So as we close this journey, let the question linger. Why is there something rather than nothing? Why does the universe sing instead of staying silent? And most importantly, it's how extraordinary that you and I are here to listen to it together across time and distance. What came before may be like asking what's north of the North Pole. The question presumes a direction that doesn't exist. Before time, there was no before, only a deeper reality where possibility, not chronology, ruled.